Hello students, how are you? I hope you all are good. So today we are going to discuss this topic, finite element for a beam element. Previously already we have discussed finite element method introduction, advantages, disadvantages, plane stress, plane strain, strain displacement relationship, as well as we have discussed finite element method for a bar element. So today we are going to start finite element for a beam element. So what is this beam element? What is the difference between this beam element and a bar element? We will see here. So see, beam is another type of one-dimensional structure. One-dimensional structure means bar element is also one-dimensional structure, right? Beam element is also one-dimensional structure. Then what is the difference between beam element and bar element? We'll see here. So see, in which the loads are applied in radial direction. Radial direction you can say, as well as you can say transverse loads. You can see here beam element is treated as bar element subjected to transverse loads, right? But if you will see the bar element, suppose this is a bar element, this load will be your like this. But coming to beam element, the load will be like this. That is only the difference, right? Otherwise we can treat beam element as a bar element also, but the bar element subjected to transverse load means whatever the analysis we will do the same analysis as we have done for the bar element, but the difference will be here the loading condition is transverse load, right? Whereas in the bar element the loading condition will be axial loading. See, this is your axial loading. That is only the difference between bar element and beam element. Both are one dimensional element only, right? You can see here I have given one example here. This is P1, load is acting here at this point. P1 is your point load, and this you can see this is UDL, uniformly distributed load. Let's say this is W, and this R1 and R2 is the reactional forces, right? This is the reactional forces. This is an example of a beam element, right? So first, what we will see the shape function of beam element. Already we have seen that, but again we will see that shape function of beam element, how we will derive the shape function for a beam element, and then we will go for the stiffness matrix, global stiffness matrix for a beam element, and then we will move to the problems analysis of your beams using FEM, finite element method. So let's go for the shape functions of a beam element. Shape function of beam element. Okay, so let us consider a beam here. This is the beam, right? We have considered a beam here. This is your V1 vertical displacement. This is your V2. Here you can see this is theta1, and here it is, this is theta2. Obviously, this is your node number 1 and this is your node number 2. If you will see a beam element at a node, there are two types of displacement. We are coming to the bar element, only one type of displacement will be there, right? Vertical displacement. But here you can see the vertical displacement as well as your rotation will be there at any nodes. Two types of displacement, that is vertical displacement as well as rotation. So we have considered two displacements here, V1 theta1 at node 1 and V2 theta2 at node 2. We have um, assumed that at node 1 V1 is the vertical displacement, theta1 is the rotation. At node 2 V2 is the vertical displacement and theta2 is the rotation, right? Then right here V1 and V2 are vertical displacements or vertical translations, you can say vertical displacement, right? This is vertical displacement, whereas theta1 and theta2 are rotations. Okay, V1 at node 1, V2 at node 2. Similarly, theta1 as node 1 and theta2 at node number 2. So let's consider this polynomial function V in terms of x, because this is one dimensional element, right? So in terms of x I am taking, so Vx will be your, you can take alpha 1 plus alpha 2x plus alpha 3x square plus alpha 4 x to the power 3. Let's take this is equation number 1. Already we have discussed how to select that. First will be only alpha 1 because this is a beam element. So here it will be alpha 1 plus next will be linear element, linear function. So alpha 2x, then square, then cube, right? So alpha 1 plus alpha 2x plus alpha 3x square plus alpha 4x cube. This is the function we have considered, polynomial function for this displacement in terms of x we have considered. Okay. So now what we will do here, v is your displacement, right? And alpha 1, alpha 2, alpha 3, alpha 4 are the polynomial coefficients. What are these? Alpha 1, alpha 2, alpha 3 and alpha 4? Alpha 1, alpha 2, alpha 3 and alpha 4 are constant, or you can say polynomial coefficients. Okay, or you can say constant also. There is no problem, we can say anything. Now this is the v vertical, but coming to this rotation. So what is the relation between this rotation and v? That is, rotation is nothing dv upon dx, right? Slope we have to consider dv upon dx. So if you want this in terms of theta 1, then what will you do? You will write here dv upon dx will be equal to, if you will differentiate this polynomial function, what will happen? If you will see here, alpha 1 is constant, so it will be directly 0. From here it will be alpha 2 plus here x square, so 2x into alpha 3, so it will be 2 alpha 3x plus from here 3x square, so 3 alpha 4 x square. Okay, let's check. This is equation number 2. Just differentiation of this first equation. Alpha 1, differentiation of alpha 1 with respect to x is 0, so 0 here. Alpha 2x, so differentiation of dx upon dx is 1, so alpha 2. From here x square, so x square differentiation will be 2x, so 2x into alpha 3, 2x into alpha 3. X cube will be 3x square, so 3x square into alpha 4, so 3x square into alpha 4. This is equation number 2. This is your theta, right? We have considered this. This is nothing your theta. Okay, so we have considered polynomial function for v also, vertical displacement as well as rotation also. Now what we will use? We will use the boundary condition, whatever the boundary condition are there, right? So you can see here at this node 1, at node 1, what are the boundary condition? You can see at node 1, v1, v is nothing v1 and theta is nothing theta 1. Similarly at node 2, v is nothing v2 and theta is nothing theta 2, right? So this is your node 1 and node 2. Okay, so v is nothing v1 as well as theta is nothing theta 1, and here you can see x is equal to 0, because if you will take this as length as L, then obviously here x will be 0 and here x will be equal to L as node number 2. So here x is equal to 0 and here x is equal to L at node number 2. So we have applied this. You can see here, this is your node 2, this is your node 1. These are the boundary condition at node 1 and these are the boundary condition at node 2. What we will do now, we will put these conditions in this equation, equation number 1 and equation number 2. Okay, so let's see what will happen if we'll keep this, then what will happen. Okay, just a second. Okay, yeah, so we'll see now conditions. If you will put boundary conditions in equation 1 and 2, we get what we will get. We'll get v1 is equal to alpha 1 and theta 1 is equal to alpha 2, because all x values are 0. So if you will put x values as 0 in that equation, you will get v1 is equal to alpha 1 and theta 1 is equal to alpha 2. Similarly, if you will put v is equal to v2, then what will you get? v2 is equal to alpha 1 plus alpha 2l plus alpha 3 L square plus alpha 4 L to the power cube, and theta 2 will be your alpha 2 plus 2 alpha 3L plus 3 alpha 4 L square, 3 alpha 4 L square. So these are the equations, right? We have considered these are the equations in terms of V1 theta 1, V2 theta 2. Now what we need to do, we need to transfer these values in form of a matrix. We have to make a matrix by using these values. So how will you make? So delta displacement. So what are the displacements here? At node number 1 we have two displacement, that is V1 and theta 1. At node 2 we have V2 and theta 2. So four displacements are there. Now in terms of what, we will make a matrix here. This is for coefficient. In terms of what, constant terms are what? That constant terms are alpha 1, alpha 2, alpha 3 and alpha 4, right? So for V1, if you will see, for V1 only alpha 1 is there. So in place of alpha 1, so V1 here it will be 1, except that everything is 0, nothing is there, right? So for alpha 2 0, for alpha 3 0 and for alpha 4 0. Coming to theta 1, theta 1 only alpha 2 term is there. So alpha 1 is also 0, alpha 2 is 1 and here again 0 0. Coming to V2, alpha 1 1, okay. For alpha 2 what is there? L. For alpha 3 what is there? L square. For alpha 4 what is there? L cube. So we'll write here L cube. Similarly for theta 2, alpha 1 is 0. So alpha 1 is 0. Alpha 2 is 1. Nothing is there in coefficient, means 1. For alpha 3 what is there? 2L. So 2L. And for alpha 4 what is there? 3L square. So 3L square. So we have developed this matrix, displacement matrix. We have converted these equations into a matrix form. Now we know if you want to find the shape function, what we need to find? We need to find this alpha 1, alpha 2, alpha 3, alpha 4. We need to make this as a subject. So if you will make this as a subject, this matrix will go downside. So we need to find the inverse of this matrix, right? So we'll find the inverse of this matrix. As we find the inverse of this matrix, we will get the value of alpha 1, alpha 2, alpha 3 and alpha 4. So let's see. If you will write here alpha 1, alpha 2, alpha 3, alpha 4, I am making this as a subject. So this matrix, we have made this matrix 1 0 0 0 0 1 0 0 1 L L square L cube 0 1 2 L 3 L square into V1 theta 1 V2 theta 2. We need to find the inverse of this matrix, right? So we need to find the inverse of this matrix. If you will find the inverse of this matrix, then obviously we will get the value of alpha 1, alpha 2, alpha 3 and alpha 4. As we will get this value, we will put in equation number 1. We will find V1, V2, V3, V4, means we will find the shape functions, right? So from here we need to find alpha 1, alpha 2, alpha 3, alpha 4. So we need to find the inverse of this matrix. If you will find the inverse of this matrix, that will be your, if you will see the inverse of this matrix, then it will be in the form alpha 1, alpha 2, alpha 3 and alpha 4. This inverse of this matrix will be your 1 0 0 0, here again 0 1 0 0, here it will be minus 3 by L square, here it will be minus 2 by L, minus 3 by L square, here it will be minus 1 by L, here 2 by L cube, 1 by L square, minus 2 by L cube and here 1 by L square. Okay, so this is the inverse of this matrix. This matrix is nothing, inverse of this matrix. You can find the inverse of this matrix into this V1 theta 1 V2 theta 2. So now we have developed a matrix in terms of alpha 1, alpha 2, alpha 3, alpha 4. Just we need to replace these values in equation number 1. Once we will replace these values, we will get the V matrix, right? In terms of shape functions n1, n2, n3, n4, because four displacements are there, then obviously four shape functions will be there, n1, n2, n3 and n4 will be there, right? So let's go for that. Just we need to replace this. In place of this, we will replace this total value in equation number 1. We'll see that how we will replace. We know the equation, first equation, V will be nothing, 1 x x square x cube into alpha 1, alpha 2, alpha 3, alpha 4. How we have written this equation? Because we have considered V as alpha 1 plus alpha 2x plus alpha 3x square plus alpha 4 x cube. So if you will write it in a matrix form, then alpha 1, alpha 2, alpha 3, alpha 4. What is coefficient here? 1. So 1. Alpha 2 coefficient x, so x. Alpha 3 coefficient x square, so x square here. Alpha 4 coefficient x cube, so x cube. And this is alpha 1, alpha 2, alpha 3, alpha 4. So we can write this equation in this matrix form. Now what we will do? We will replace this alpha 1, alpha 2, alpha 3, alpha 4 because these are the constants, right? We don't know this value. We need to find this value and we will replace here. So we found this value in terms of that matrix, right? Displacement. So your V matrix will be now, it will be in the form 1x, x square, x cube, and that matrix is 1 0 0 0 0 1 0 0 minus 3 by L square minus 2 by L minus 3 by L square, then minus 1 by L, and here it is 2 by L cube, 1 by L square, here minus 2 by L cube, and here 1 by L square into V1 theta 1 V2 theta 2. So this is the matrix we got. Just multiplication. What we need to do? Multiply these terms. 1 into 1 will be 1, right? Again, x into 0, 0. X square into this. So minus 3 by L square into x square. X cube into this, 2 by L cube into x cube. So if you will multiply like this, then you will get V in terms of this matrix will be like this: 1 minus 3x square upon L square plus 2x cube upon L cube. This one, right? Now again we will multiply with second column. So 1 into 0, 0, 1 into x, x square into minus 2 by L. So minus 2 by L x square, x cube into 1 by L. So 1 by L square into x cube. So second term will be x minus 2x square upon L plus x cube by L square. Third term is third column. With third column, 1 into 0, 0, x into 0, 0, x square into minus 3 by L square into x square, and x cube into minus 2 by L cube. So you will get here 3x square by L square minus 2x cube by L cube. Similarly, for fourth column, you will get minus x square by L plus x cube by L square into V1 theta 1 V2 theta 2, right? So these are your shape functions. Let's say this is n1, this is your n2, this is your n3, and this is your n4. These are the shape functions. n1 is for v1, n2 is for theta 1, n3 is for v2, and n4 is for theta 2. These are the shape functions, right? If you will compare, then obviously you will get the matrix will be v will be equal to shape function is denoted by n, because these are n1, n2, n3, n4 for different displacement, into delta. Delta, what are the delta? V1 theta 1, V2 theta 2 is the delta only, right? So we need to find this. So we already found this n values, n1, n2, n3, n4 we have calculated here. So just we will write here. So your n1 value, what is your n1 value? 1 minus 3x square upon L square plus 2x cube upon L cube. Similarly, what will be your n2 value? If you will see this n2 value, it will be x minus 2x square upon L plus x cube upon L square. Similarly, n3 value will be 3x square upon L square minus 2x cube upon L cube on L cube. And n4 value we have calculated as minus x square by L plus x cube by L square. So this is your n1, n2, n3, n4. These are the shape functions. Shape functions. Okay. So we have calculated these shape functions. Now coming to this shape functions we have calculated for beam element. So this for this a special name is there. This is also called as Hermite shape functions. Why Hermite shape functions? Because some conditions are there. If these shape functions are following that conditions, if that is following, okay. So what will happen if that is following means this is also called as Hermite shape functions. Just we need to check whether that condition is followed by these shape functions or not. What are that conditions? Just I will write here condition, and just we will check whether it is following or not. Condition is for Hermite shape function. Hermite shape function. What are the condition? Condition number 1. If you will see at node 1, at node number 1, because for beam element 2 nodes are there, so at node number 1, if you will see, n1 will be 1, and except that n2, n3, n4, these will be 0. Coming to this, dn2 upon dx will be 1, except that everything will be 0. dn1 upon dx will be equal to dn3 upon dx, dn4 upon dx will be 0. Similarly, at node 2, if n1 is equal to n2 is equal to n4 will be 0 and n3 value will be 1, and similarly dn1 upon dx will be equal to dn2 upon dx will be equal to dn3 upon dx will be equal to 0, and dn4 upon dx value should be 1. If this condition is following, if these shape functions are following this condition, then we can say that this is also called as Hermite shape function. So how we will check? See, at node number 1, at node 1, what is here? X is equal to 0. So if you will put here n1, x is equal to 0, so this term will become 0, this term will become 0. So at node 1, I am writing here at node 1, so this n1 will become 1, right? This term will become 0, this term will become 0, as we will put x is equal to 0. For n2, x is equal to 0, 0, 0 means we will get 0. 0 means 0, this is also 0 term, this is also 0 term, so we will get 0 here. For n1, n4, we will put x is equal to 0 for at node 1, so it will be again 0. So see, first condition verified. n1 is equal to 1, and except that all values are 0. Now coming to dn2 and dx. Now if you will differentiate it, right? So dn1 upon dx, if you will differentiate, this term will become 0, and here also it will be term of x, here it will be the term of x, right? So if you will put x is equal to 0, again this term will become 0. Just see, I will tell you, dn1 upon dx, if you will find, what will happen? This is 1, so 0 minus 3x square upon l square, so x square is 2x, so 6x upon l square, plus 2x cube means 3x square, 3 to the 6x square upon l cube, 6x square upon l cube. Now we will put x is equal to 0, what will happen? This will become 0 and this will also become 0, so this is 0 only. Now coming to n2, this term is x square, this term is x cube, so this will become 0 only. After differentiation also, this will become your 4x and this will become your 3x square. So obviously if you will put x is equal to 0, this term will become 0. But coming to this first term, dx upon dx, that is 1. So n2 value you will get, dn2 upon dx value you will get as 1. Except this also only, these two are the x terms, 0. These two are the x terms only, 0. So these two terms also you will get 0 only. So only we are getting dn2 upon dx as 1. You can see here dn2 upon dx as 1. And dn1 upon dx, dn3 upon dx, and dn4 upon dx is equal to 0. We are getting the same thing here, right? So the condition which are given for node 1 is following. Now we will check for the node 2. So if similarly, if you will check for node 2 also, it will be same. So I will check here for node 2. For node 2 also, I will check the conditions. Okay, so that we can identify whether this is Hermite shape function or not. At node 2. So at node 2, what is there? X is equal to L. Now if you will put here x is equal to L, so L square cancel. It will be minus 3. See, if you will put here L, then it will be L square. So 3L square upon L square, L square cancel. So 1 minus, it will be 1 minus 3 plus here L cube cancel plus 2. So it will be 0, right? Coming to here, x is equal to L. So if you will put here L, here if you will put L, so this will be your L minus 2L square upon L, 2L square upon L plus L cube upon L square. So this will be L only. This will be L only. So L minus 2L plus L. So again it will be 0, right? Coming to this third one, if you will put L here, so L square cancel 3. minus L cube cancel, minus 2. So the value become 1. So you can see here N3 value is 1, N1, N2 is 0. Now coming to N4, if you will put here L square, no, minus L square upon L, so minus L square upon L plus L cube upon L square. So cancel it, this will be minus L and this will be L plus L. So the value will become 0. So except N3 is equal to 1, everything is 0, N1, N2 and N4 is 0. Similarly, if you will check for this condition, you will get the same. So if these conditions are followed by these shape functions of two noded, what type of beam I have taken? Two noded, because I have taken only two nodes, right? So two noded beam elements. For two noded beam elements, whatever the shape functions we are getting, that is also called as Hermite shape functions, because it is following the condition for Hermite shape functions, right? So this was the shape functions of beam elements. So we have calculated these shape functions. We know the usage of shape functions. If you want to find the displacement, deflection at any point on the beam except that nodes, then obviously we will use these shape functions to find that deflections, right? So in next session we will discuss about the stiffness matrix for beam element. Okay, so thank you for joining the class. We will see the stiffness matrix for two noded beam element in the next class. Okay, so thank you.